welcome to this public lecture on behalf of the New York Abu Dhabi Institute on multimedia mobile devices by Professor Wolfgang Effelsberg from the University of Mannheim, Germany. Tonight's event is known in the Institute workshop, a public component of a 2 days workshop on advanced next generation multimedia research and development. And we have 25 speakers from all around the world discussing and providing ideas about the latest development in research, in industry and research institution. It is, as you know, the NYU Abu Dhabi Institute is providing the support for this workshop because we think that the United Arab Emirates can, will, and should play a vital role in tomorrow's advancements of technology. If you allow me to introduce a bit Professor Wolfgang Effelsberg, who received his diploma back in '76 from Darmstadt, the Technical University of Darmstadt, and his PhD degree in '81 from the same university in Germany in computer science. He worked in the United States from '81 to '84, where he was assistant professor at the University of Arizona in Tucson, and then an IBM research fellow in San Jose, California. In '84, he returned back home, Heidelberg, not Mannheim, but it's just a few kilometers away, where he joined IBM newly founded European Networking Center in Heidelberg. From '84 to '89, he led the research group there, working on the design and implementation of communication protocols and application. In '89, he joined the University of Mannheim as a full professor, where he is the chair of practical informatics, and he is basically supervised, I don't know, but probably more than 100 PhDs and a couple of hundreds of master's students in the multimedia communication and networking. He served for several years as vice chair of ACM Multimedia Special Interest Groups, where he was leading figures in deciding about the future of the multimedia. He was also one of the founding members who pushed the multimedia field in the ACM and IEEE through the introduction of ACM transaction on multimedia tools, on multimedia communication, and ACM transaction on multimedia, TOMCAP. He published several vital books on multimedia compressions and networking, and I mean, I really don't know the number of his seminal journal paper and reference paper published in very highly cited journals, just because on a daily basis he has something new. So it's very difficult to follow the advancement of Professor Effelsberg's progress and career. So I am very happy and I'm very pleased to have him here tonight as our public lecture speaker, and I thank him in the name of NYU Abu Dhabi Institute for accepting this invitation.
First of all, I'd like to thank you and also Professor Sunil Kumar for inviting me here. It is amazing to see the progress of the city and the country. It's really impressive, so it's quite a good experience for us. My talk tonight is about multimedia on mobile devices, and Abed told me ahead of time that this will be a public lecture, so I have very little mathematics in it, so that should be understandable to the general public. So this is the content of what I wanted to talk to you about. First of all, I present you a motivation why I think it's important to do research on multimedia on small devices. Second, I'll talk about scaling and cropping. These are two techniques that you typically use when you want to shrink a video to the size of a mobile phone. And I'm also showing you why this is not good technology. This is used much, but it's not a good technology. Then I'll introduce to you the concept of seam carving for still images. And then I'll talk about an improvement for seam carving for diagonal lines that show up in a still image. Then I'll talk about seam carving for video. This is where we have done more recent work in our group. And I'll show you some video examples on how this works when you want to shrink a video from a large screen to a small screen. And then I'll conclude and give a brief outlook on future work. All right, let's begin with the motivation. Multimedia on small devices is obviously interesting because the small devices are so important nowadays. Mobile devices, smartphones, pad computers are getting very popular nowadays, and in particular for showing videos. The prediction for showing videos via the internet is tremendous. This is the most quickly growing area of all the application areas in multimedia. So in 5 years, everybody will produce videos on their small devices, on their mobile telephones, their smartphones, and they want to share that information also. So I believe that it's really relevant to take care of that new progress in the field right now. The representation of still images and videos on those devices, on the handheld telephones especially, requires an adaptation of the screen size and also of the aspect ratio. So it's not just the size of the screen, but also the aspect ratio. So if a video was produced with a large screen in mind, say HD television, and you want to shrink it to a small device with a different aspect ratio, you have to do something to the image or to the video. And we'll talk about that in a moment. Scaling and cropping are the two techniques that are used nowadays, even for television sets, when you want to go from HD television to an old-fashioned television set, or from HD television to a laptop computer or to a smartphone. And I'll tell you in a moment why they do not work well for that purpose. Fortunately, seam carving was invented in 2009. It was published at ACM SIG Graphics, the famous ACM Graphics conference, by Rubinstein and Shamir. And so I'll introduce you into the idea of seam carving, and I'll try to do that quite slowly so you get the idea of what seam carving really does to an image. Okay, so the rest of the talk will then concentrate on the details of seam carving, how you can adapt that to video, how you can remove artifacts from that, and so on and so forth. All right, so how does scaling work? In scaling, you reduce the image linearly without looking at the content. Okay, so you shrink it in all directions until it fits into the final screen. So if you have an HD television video, you want to show it on a smartphone, you shrink it until it fits on the screen. If the aspect ratio is not right, you use letterboxing to make it fit. You see that here. You have a black stripe on top and a black stripe on the bottom, and the real content of the image is shrunk in this way. Okay? Now, this is obviously not a good idea because the image gets so small that you can't see details anymore. Like in this example, it would be much better to show the people that talk to each other than to show the gray wall in the background. So obviously just shrinking it linearly is an easy thing to do, but it's not optimal for the purpose that we have in mind. Another alternative is cropping. Cropping means you cut around the borders. Okay? You cut the image parallel to the edges until the final format is reached without looking at the image content. Okay? And of course parts of the image can get lost. In this example we see when we crop the original image, we cut these two people in half. That's not very pleasant either. And we leave the gray wall in the middle unchanged because we don't look at the content of the image, but we just do something that can be done with any image without looking at the content. Okay? So that's not a very good idea either. So the basic statement of this talk is that we should look at the content of the image and we should cut off those pieces from the image that are less relevant to the human viewer. Okay? And that is what seam carving does. Seam carving for still images is a technique that removes specific pixels from the image based on the importance of the content to the human viewer. Okay? So if we look at the example, we would cut out parts of the gray wall and leave the people in the image. That means that we have to look at the content and automatically do this cutting out. Okay? So how do we do that? We have to compute an energy function that describes the importance of the different parts of the content. And then we cut out the parts of the image that have a low energy and we leave the pieces that have a high energy in the image. In this way, we can concentrate on the important parts as we watch the video later on. Okay? Now, let's look for a moment at how we would do that. So the initial ideas, you see a photo on the left-hand side. It's a clown who sits on a podium in a water fountain in a shopping mall or something. And we want to shrink that image to 40% of the original size. Okay? And in all my examples, I just do the shrinking, cutting out vertical columns, so the image shrinks sideways. But you can apply the same algorithm, of course, to cut out horizontal lines from the image. So I just use the vertical cutout as the examples, but it just works in the same way for horizontal rows. So let's assume that we calculate this energy map for the image. We come up with something like shown on the right-hand side. So the blue areas are the areas with low energy. And the red and yellow areas have higher energy. So what was used in this example to compute the energy? It was the intensity change between a pixel and its neighboring pixels. Okay? If there's a lot of intensity change, that pixel gets a high energy value assigned to it. If there's very little difference in the intensity, it gets a low energy value assigned to it. So if you have a monochrome surface like the red one here, it gets a low energy in the energy map. Okay? So the right-hand side is the energy map of the left-hand side picture, and that's what we want to use to cut the less important part from the image. So let's do that in a naive way. Okay? We look at the energy map and we cut out the pixels that have low energy. So what is the result going to look like? It looks like on the right-hand side. So if we cut out the pixels with the minimum energy, we get such a blurry image. Why is that so? Because the energy pixels with low energy are in different parts of the image all over the place. Sometimes they're on the left-hand side, sometimes they're on the right-hand side. So they're in different places all over the image. If you cut them out, you get an unrecognizable image. So that's not a good idea. So what would be the next better idea? If you think about it as a computer scientist or an image processing person, you would now come up with the idea to cut out columns. So you compute the energy of a column that goes from the top to the bottom. You would compute the energy of the entire column as the sum of the energy of the pixels. And you would cut out these columns one after the other until you've reached the final shrunk image. Okay? So let's look how this works. We now remove 200 columns with the smallest energy from the image. And that looks already much better. Okay? So we still see the clown, we see most of the image, but we get these strange curves in here. So this straight line in the original photo gets represented with the curvature as shown in this picture. So why is that so? That is so because typically adjacent columns are cut out that have small energy. And if you cut out adjacent columns from this image here, you cut out a piece of that diagonal line also. Okay? So when it was a straight diagonal line before, it becomes a curved line afterwards. So just cutting out columns is already a better idea than just removing pixels with minimum energy, but it's not a good solution yet. Okay? So the key idea of Rubinstein and Charmier in 2009 was the definition of seams. Okay? A vertical seam, we take vertical seams as examples, as I said earlier. A vertical seam is an 8-connected path of pixels running from the top to the bottom of the image and containing exactly 1 pixel per row. Okay? That's a natural representation of a seam. Okay? 8 connected means that you go either right or left down, so diagonally left or right down, or straight down, straight up, and so on. So you get a seam that looks like this in the example. So, and then we simply compute the energy for those seams, and we cut out the seams that have the smallest energy. Okay? So what is the main advantage of those seams over just having vertical columns? The main advantage is that these seams can adapt better to the objects of interest. Okay? So if you have an object of interest in the middle of the picture that was not visible in the top row and not in the bottom row, but it's in the middle, that seam can go around that object of interest in the middle. Okay? So if we have 2 objects like the red ones shown here, the seam can move around those edges, so those objects. Okay? So it can stay in areas with minimal energy under the condition that they are still 8 connected. Okay? So if we now use seam carving for the original image, this is what comes out. Okay? We have again cut 200 vertical seams this time, not columns but seams, with a minimal energy, and we have an easy computer science method I'm not going to present here, that computes the seams with minimal energy. It's just a computational problem. You can imagine how this can be done. Okay? So when you cut out the 200 vertical seams with a minimal energy, you get this photo as a result. So you see this is shrunk by 40% if you compare the entire width of this photo with this photo, and it still contains pretty much the same content, except when you look very close, you see some small differences. So I claim that this photo preserves the main content for the human viewer much better than all the other approaches. Okay? So where you see changes, for example, this of course was a straight column here. That column has small energy values because it's monochrome. So pretty much most of the pixels have the same color value as the neighboring pixels, or grayscale value as the neighboring pixels. So here you see that part of this column are actually cut out, because the seam that goes through here cuts out these pieces. He considers the edge pixels from the neighboring structure here to be more important for the human viewer than the monochrome pixels of the column. So that is the artifacts you see when you look really close. But as an overall impression, we can say that this image looks better to the human viewer than the other examples we had earlier. Okay? So that is the basic technique of seam carving for still images. Let's look at the other example I showed you earlier when we talked about scaling and cropping, the two people that talked to each other and had the gray wall in between. So that's the original photo again. And here we see the seams that were computed by our algorithm. Each red line that goes from top to the bottom is one seam. Okay? So you can see that you would probably, as a human being, also take a seam that goes through here. There's just one area where you have a high energy, where this edge is in the photo, or you would cut out a line here in that part of the image, where you would just have a high energy piece within 2 or 3 pixels here. The rest of it is pretty much monochrome, and therefore it's a good idea to cut out seams there. Whereas this object here has sharp edges, and so have the sweaters of these two people and so on, so you leave those in place because they have a higher amount of energy than the rest of it. So these are the seams computed by the algorithm. When you cut them out, this is what you get as a result. Okay? So this is obviously a good algorithm to remove unimportant parts from the image, at least as a basic idea. Now, we have to talk for a moment about the energy function, because that is the most critical part of it. If you have a bad energy function, you don't cut out the right parts of the image. Okay? So the initial approach that I've showed to you in the photos we have seen so far was simply based on the difference in the lighting, in the light intensity between neighboring pixels. Okay? So if the light intensity or the grayscale value of a pixel is the same as that of its neighbor, or just has a small difference between itself and its neighbor, that would be a candidate for cutting, for minimum energy, and that would be cut out. So we can write that down as the energy of the intensity at pixel xy in the two-dimensional photo is the gradient in the x direction plus the gradient in the y direction of the energy values. Okay? So that's the slope, so to say, when you look at the grayscale image as being a landscape, mountainous landscape. The gradient is the slope in the landscape. So if two have the same grayscale value, they have a low energy, and that means they are candidates for cutting out. So we can think about better energy functions, and I'll show some of you to those of you in a moment. Okay? Because the better the energy function is, the more precisely we know which parts we can cut out of the image in order to produce a most interesting result to the human viewer. Okay, and here are 2 improvements, okay, that we can do. The first improvement is that we can actually draw saliency maps. And saliency maps, the technique is well known from image processing. Saliency maps tell you what the most relevant parts of the image are, and they were developed independently of the seam carving work. Okay? A saliency map tells you what the important areas are, but they are again based on physical properties of the image, such as the sharpness of the edges and the gradients and so on and so forth. And the other thing that we can use is we can try to use object recognition. So if we have an algorithm that recognizes faces or facial areas in the photo, we can give a higher priority to those faces and say, probably the viewer wants to look at the faces. So we want to protect the faces from getting low energy assigned to it, and we can use face detection and put a high energy preference to those face detections, for one example. You can also use other kinds of object detection if you're interested in cars. We saw Joachim Schaper's presentation. He had cars in there. He followed the cars through the streets. So you can also use cars if you're interested in cars. So any type of object recognition would help you to get a better energy function. So in this example, we have an improved energy function, which has the same intensity value at the end, the gradients in the x direction and the y direction, plus we have a weighted function that weighs the fact that a face appears here, plus a weighting function for the saliency that is also computed for this image. So if we take the Lena face that is much used in computer graphics, everybody who's ever studied computer graphics knows this picture here. That's a photo of Lena. And if we compute a saliency map for her, this is what the saliency map looks like. So this is just background information. It doesn't count much for the human viewer, whereas the head and the face, they count more. There's more important information in here. The second component, the face, we've used face detection. And the face detection is a well-known problem. We can say that it's pretty much solved nowadays. Even if you have a photo camera, the photo camera can do face detection. They can at least find the regions that contain faces in a photo. That's pretty much standard today. So we can run face detection, and we find out that in this area here of the original photo, there was a face. So we value that area very high by putting a face map over it, and that protects the face from getting low energy assigned to it. So if we run that improved energy function here, we get the following seams. It's kind of hard to see, but we have the red lines again here that run through this image, but the face is completely protected. So when we restrict the size of the photo to, say, 50% of the original size, this is what we get. It looks pretty natural because the face was protected, the salient features were protected, and the rest of it was deleted. So that is how we can use an improved energy function to compute those seam carving results. Now, still, when you do all I've said to you so far, we have a problem with diagonal lines. If we have horizontal lines, no problem at all. The algorithm just runs through them. If we have vertical lines, no problem at all. Either they are monochromous and then they cut out, or they have many different textures in it and they stay. But diagonal lines are a problem. And we found that out when we ran the algorithms in our lab. So we have these rails of this tramway in Mannheim, and they are diagonal lines. So if we take this original image and we run whatever we've seen so far, including the improved energy function, this is what we get. So you don't want to run your train on these rails here. It's not a good intact rail. So that is a problem we have if we do standard seam carving on images that contain diagonal lines. So we were surprised to see that, so we looked at it and we found out that the reasons for these damages to diagonal lines are the following. If you have a diagonal line in the image, that's the original size image here, and you run your seam carving algorithm, probability is pretty high that several seams that run from top to bottom run through the same area of that line, because that's an area where the energy above the line or below the line is small. Okay? If the energy here is small and the energy here is small, the lines, the seams will go through that line in this place. So we get multiple seams going through the same place of that line, and that's the result, of course. The photo is moved together and the lines are cut out there, and so you get these curvatures into the lines. So there's nothing you can do about it, you think. So we have proposed in a recent paper to make those seams move away from the critical points. Okay? So the idea is, this is especially critical if several seams cross the line at the same place, as we saw in the previous example. And now our idea was to distribute the seams more evenly over that line. So if you have a diagonal line, we don't want all the seams to go to the same point, but we want them to be distributed more evenly over the diagonal line. Okay? How do we do that? Well, we have a first seam that goes to the line in this place. But once we have determined the point where that seam crosses the line, we change the energy function. So after we have computed one seam, we change the energy function by putting a Gaussian distribution over it that has the maximum at the point where the seam crosses the line. And it's decreasing towards the outside. Okay? So that Gaussian function is like a mountain that has the maximum in the point where the seam crosses the line and decreases towards the outside. So that is the changed energy map, energy function for this photo. And that means when we run the next seam through that image, it doesn't go to the same place anymore because it has the energy has increased in this area. So it runs through a different place. We put another changed energy around this place, and in this way we force the lines to move to different points where the diagonal cuts through the image. Okay? Now let's look again at this tramway in Mannheim. So this was the original image. That is when we did traditional seam carving, and this is what we get out when we have the improved seam carving, where we prevent several seams going through the same point of the diagonal line. Okay? Of course, you have to run a line detection algorithm beforehand, but line detection can be done. It's well understood how you can compute straight lines in photos. Okay? So that is an improvement that we have added to the seam carving for still images. Of course, you can do many more things. We are still working on those. So you can probably improve much more than just this example. All right. Now, that concludes the part on seam carving for still images. And I now come to the topic of seam carving for video. You might say this is easy to do because a video is just a sequence of frames. So when we know how to do seam carving for a single frame, we simply apply the same seam carving idea for all the frames that we've done. Okay? So what would happen if we did that? Well, the video changes from frame to frame. For example, a car runs through the image. That means that the energy function changes as the video runs. Okay? That means that the priority of running the seams through the image changes also from frame to frame. Okay? So if we decide to run a seam through here, say, because it has small energy, a moment later the car will be in that place, and the car creates sharp edges that creates high energy areas, so we can't run through that area anymore. So we compute a seam for another place. So we did that. We have done that computation for a video, and here's what you get out. So this is just the first naive approach, so to say. You see the video gets really shaky, because for every frame, the seams run to different places. Okay? Oops. So we can look at that again. So it would not be a good idea to process video this way. So if you want to watch a video on your smartphone, a video of a famous German soccer game, as we talked about earlier today, then you would hate to watch that video if it was processed in this way. So we have to reconsider the problem of seam carving, especially for videos. Okay? So there was an initial approach published by somebody else, also again by Rubinstein and Shamir, the people who invented it originally in 2011, and they proposed to do the following thing. They simply consider the video as a block of frames, one put after the other. Okay? So every frame is a single image, two-dimensional image, and the video is just represented as a block of single frames that are stacked up. Okay? And then they say they want to compute surfaces that go to that block, but they must be connected. So say that a seam is computed for the first frame that runs through here, and that seam must be represented again in the second frame and the third frame, and again they ask that in the third dimension, in the temporal dimension, they must not be more than 1 pixel away from the previous dimension. So in this way you get a surface that goes through the block in the time direction, and that allows you to cut out these surfaces one at a time. Now you can process it in this way, and it works pretty nicely, but it's very computationally expensive. So you compute forever for a relatively short video. So we have come up with another idea, the second idea, which we call fast seam carving. If we do that, we simply map all the frames that belong to the same video shot into one frame, into the first frame, say. We map everything to the first frame. If we have panning or zooming, we have to compute a wider frame, of course. And then we do our seam carving in the first frame, and then we map the seams back into the time dimension. And that is much faster to do. Okay? So we accumulate all energy values of all frames in one frame, say the first. We compute the optimal seams here, and then we map those back into the block of frames afterwards. Okay? So the effect is the same, that we don't take out seams anywhere in the images, but they have to be connected. Okay? Now let's look at the result. On the left-hand side, you see the naive approach, where we have just computed seams frame by frame. And on the right-hand side, we see fast seam carving that I've just described to you. Okay? Oops. It doesn't seem to run. Well, anyway. Well, what you would see here is that on the left-hand side, it shakes as it did before. It's the same shaky image we've seen before. And on the right-hand side, you see a pretty stable video. It just looks nice. It's just a shrunk video with some pieces cut out, but other than that, it is a good quality video. We can look at that again with this example here. I'm sorry that it did not work in the previous one. I don't know what went wrong on this PC, but it happens sometimes, so something might have gone wrong. So if we look at the video with the two people here, where we cut out the seams in the middle, we have to use the same trick here. We have mapped everything into the first frame. We have decided on the frames with the seams with the minimum energy in the first frame, and then we've mapped back those beams into the temporal dimension. So if we do that, you see the original video on the left, and you see the smaller video on the right-hand side. Okay? So you can say that in the left-hand side, we've used scaling. I told you what scaling is. It just means that you shrink everything into one dimension. So if we had the original video as a HD television video, say, so it's a pretty wide video, we've shrunk it by moving it in this way. So it's scaled. You see that the people tend to be pretty slim. They would be envious of being so slim. So they are slim anyway. These are two PhD students from my lab. So they were kind of compressed a little bit. In the left-hand side, they were scaled. And on the right-hand side, they look like they naturally look. And so that's a more pleasant video to look at. All right. So in more recent work, we have looked again at the problem of the amount of seam carving you can do in one image. And that is, we can get to about, say, 40% of the original size without too many problems. But if you try to shrink an image by much more than 60% of the original size, then the seams run through important parts of the image. So now we have developed a new algorithm that stops carving out seams when it finds out that it touches important regions. Okay? So it is adaptive in the sense that it won't cut out important regions, but when it finds out that it can only run seams through important regions, it goes over to scaling. So it's a combination of seam carving with scaling, where we do as much seam carving as would be reasonable for the human viewer, and then we do scaling. And that gives an overall good performance of the final result. Okay. So let me conclude and give you a short outlook. First of all, seam carving, as we see it, is a useful technique to reduce image sizes without losing relevant content. Okay. Finding a good energy function is a real challenge. I've presented to you an improved energy function that has the phase detection built in and the saliency maps built in. But of course, you can go further. You can try to improve even more improved energy functions for still images and for videos. Improvements are possible for diagonal lines, and I've shown you that. And you might also come up with other improvements for other typical artifacts that the seam carving creates. Now, flicker removal is of critical importance for videos. You cannot simply do the naive approach, because otherwise you get this swimming image. And fast seam carving is a useful algorithm for that problem. Okay. Now, what are the limits of seam carving? The limits are reached when you have a photo where every area is equally important. Okay? If you look at a flower bed with a lot of beautiful blossoms, it's hard to tell for the human user where you would run the seams through, because every little blossom has the same importance. If you have photos of this type, seam carving is not the right approach. Then we've just got to go ahead and use scaling, because then the damage that's done by scaling is not as bad as the damage that you would do if you cut out seams using seam carving. So clearly seam carving has its limits with these types of images. Okay, it does not work well when most of the content is actually relevant for the human viewer. And seam carving can be combined with other techniques, as I mentioned, to create a pleasant small screen version, especially when seam carving detects that it would run through high energy regions if it continues to cut out seams. Okay, so that's about all I wanted to tell you. This is my email address. I'm effelsberg@informatik.uni-mannheim.de. If you need further information, if you want to read our papers, you can look them up. They are on our web pages. But you can also write me email. I'll be glad to answer any questions you might have. All right. Thank you very much. Thank you.
So I'm wondering, is this something that you envision actually taking place on the mobile device, or is this something that would be used to process the image or the video before it's sent to the mobile device? It actually seems like it's pretty processor intensive and may not work so well on a mobile device. Yes,
you're right. It is pretty processor intensive, that's right, because you have to compute these minimum seams. And also, you want to save bandwidth. If you transfer the image first and then you compute a reduced version on the mobile device, you would need more bandwidth to communicate. So we imagine this to happen on the server side. Either it's a live server or it's a stored video server, but it would have to be done on the server side before transmitting the video. Right. That means that you have to communicate the final size of the device to the server side so you can do the right computation. Yes.
And my second question is, and I'm sorry for hogging the mic, I'm wondering, has there been any studies done on sort of the perception of the user with this versus other techniques? Do users have any sort of preference, perceptual preference with these various techniques? And I'm just curious.
Yes. Yes, we've done user studies with real users, not only students but also other users. And for the papers we wrote ourselves, we've always done such user studies. And in general, they found out that our approaches are useful and are pleasant to look at, except when we touch high energy areas. So that's when then they rate traditional techniques better than seam carving. But for the other types of photos or videos, they found our techniques better. So we just didn't tell them which one was our video, which one was produced by another algorithm. They looked at it and they just voted for the better ones, and then from that we derived that they liked our algorithms.
Are there any benchmarks available on the computing power that is necessary to do that kind of downscaling?
Yeah, that's a good question. I don't have them here. We have done it, but I don't have them here. So I can't tell you how slow it is. It does not run in real time. Okay, but we have thought about an implementation on the QDA architecture that you mentioned earlier in your talk. When you have special graphics processors, you can do some of that on the graphics processors. We have considered that, but we have not done it yet. We've done that for other work run in our lab, for example, on HDR video. We have run that on the QDA architecture with parallel processors, but we have not done that with that technology. Yeah.
There's a question on the seam. You said you have horizontal and vertical seams that are possible.
Yes.
Does it make sense to do both? If so, how would you avoid the problems that you had mentioned?
Yes. Of course, when you do that for a real video or photo, you look at the target size and the target aspect ratio of the video. And if you have to shrink it horizontally by 50%, you run seam carving in that direction by 50%. If you want to shrink it vertically by 30%, you then run seam carving on the vertical part and do that by 30%. So it's orthogonal. You can do it in 2 dimensions independent of each other. But of course, normally you have to do it in both dimensions. I just picked 1 dimension for illustration for this talk.
My question was that if you need to do it for both the dimensions,
yes.
If you do it sequentially, then you may run into problems that you had mentioned. So would you like to avoid some edges by doing them like concurrently?
I think even if we do one after the other, we remove the vertical seams first, then we remove the horizontal seams, we run into exactly the same problems that we run into right now.
Yeah, so anybody who does photography will tell you that, images usually have certain interest areas, for example, the 6 points which are supposed to be uniformly distributed on the image. Those are the points where basically most photographers put the most interesting stuff, and if they are shifted sideways, or if the ratios are distributed, you are actually reducing the quality of the image significantly because people cannot put at the correct attention points. So did you guys look at more uniform distributed skylines, sorry, not skylines, the seam lines, to make sure that these ratios are not significantly affected?
Yeah, that is a very good question actually. When you have lots of objects that move through the image like crazy, so there's an Arnold Schwarzenegger movie where he jumps with his motorcycle and a big explosion occurs and lots of things happen at the same time. Lots of objects move at the same time in the video. You will not find any seams that you can run through low energy areas. So the answer would be, our algorithm would give up right from the beginning. Because if you have too many moving objects, you have no chance to find seams in between. Especially if you have a longer shot between two cuts, and you have moving objects within this shot, you have no way to find seams that would be compatible with the video idea. Yeah. But if it occurs between shots, we can do it. So if it's within one shot, we can do our computation. If you have motion in the first shot, then you have a cut, you have motion in the second shot, we can run our algorithms. But if objects move through the image all the time within one shot, then it's not going to work. Yeah.
Thank you, Professor, for the nice lecture. Just a question. Talking about video, if we've got video standards in terms of aspect ratio like 16:9, or if we've got standard aspect ratios for videos, and most mobile phone screens also follow same aspect ratios, where do you see real-life applications of the seam carving for videos?
So the question is, we have pretty much standard aspect ratios for television nowadays, and the mobile phones also tend to come up with the same aspect ratios. I don't see that yet. It might be in the future, so that when you turn a phone sideways, you get pretty much the same aspect ratio as you have on a high-definition television screen. But even when that happens, we still have the problem of reducing the size. So even if the aspect ratio is the same, you can't have as many pixels. You won't have a 1980 by 1080 pixels on a small screen, at least not in the near future. So that is, and even if you have them, you hold your smartphone much closer to your eyes. So the critical part of the resolution is the angle that the human eye can resolve. If you sit 4 meters away from a television set, you have a certain viewing angle. And if 1980 by 1080 is a good resolution for the television set, even if you were able to create a small size screen that had a 1980 by 1080 resolution, it would not be useful for your eye because you can't resolve that angle at a small distance. So I believe that at least the size reduction will always play a role, so that technology is going to be worthwhile even when we had, if we had smartphones with a high resolution of HD television.
Hi, Professor. Does the same technology apply to increase or enlarge images?
Okay. Yeah. So the question is, does that same technology apply to increase the image? And I say yes. And what you do in order to increase the image is that you run the same scene through it. And if you find a good seam, you duplicate the pixel values in that seam. So it's not a perfect, or you can interpolate. So yeah, if you find a good seam and you want to increase the image, you interpolate between the adjacent pixels, or a simpler method would simply be to duplicate the content of the seams. But interpolation is a better technique. So you can use the same technology in the inverse way by starting with a small screen and then blowing up the image. That's possible, yeah.
One could say that creating an image or shooting a video is an artistic creation, so therefore a form of self-expression. Have you looked into asking the content producers which algorithm affects their creative integrity the most and the least? What do the content producers say?
Okay. Of course, if you look at objects of art, you look at a Rembrandt painting, he would be upset if you do things like seam carving on his painting. So my answer would be, if it's artistic work, no matter whether it's artistic film or artistic still images, you might run into problems with the authors of the work. So if I create the Scream, and I'm Edward Munch, and I create the Scream painting, and people would do seam carving on the Scream painting, I would be really upset. So my answer would be, I would rather not do that on objects of art, unless you show it to your kids and they don't care. You know. But for the serious user, I would probably not do seam carving on objects of art. Yeah.
I have one question following the debate on doing seam carving or not on Rembrandt. But exactly which kind of video you think can benefit of this technology? Because I was thinking about, there's the saying, a camera doesn't lie. But in the example that you've shown, for example, something as innocuous as the distance from, the piece of paper from one of the two guys that were talking,
yes.
It's completely different in the new video. So
yes.
I'm watching a video that yes. doesn't convey any substantial, factual, real information I can rely on. Yeah. So this presents actually a problem. Do we need something like a caveat? Okay, this video has been seam carved or something like this.
Okay, that's a good
Thank
remark.
you.
Yeah, and of course you're right that the paper seems to be bigger if it's kept in the video. Then yes. I would say that in most of the videos that we watch in the daily usage, this can be used. You can use it for newscasts. You can use it for sports events. When you watch a Formula 1 race, you don't care about the little details. Even if it is not as the camera recorded it, if it's changed. I mean, you probably know that modern television sets do terrible things to the original photos. So when you have a Philips television set, it does, for example, it sharpens the edges. This is not as it was recorded. It is artificially created so that you have an impression that this is a really sharp television set. So they do terrible things. If you send in your photos to get them processed by Kodak, they make the sky bluer. So they have an automatic sky detection algorithm. When it detects sky in the photo, it makes it a little bit darker blue. So lots of terrible things happen already to the original camera videos or photos we take. So I don't think this is just another algorithm in that direction. But I would just, my caveat would be, do not use it for objects of art. Yeah. All right.
Okay, thank you.